All right, next in the chapter are several miscellaneous examples. And I'm not going to go through this in detail. Suffice it to say, you should get some practice identifying the objective function and the constraints. And I also think it's a good idea to put things in a table like I did here. It's good to get practice doing that. So here's a diet problem. Here's a manufacturing problem. Transportation problem. And here's a nice way to diagram it. So you can read through this in detail. It's very clearly explained. And down here is a summary. All right. So a linear programming problem is one that's concerned with finding the optimal value of a linear function of several variables, called the objective function, subject to the conditions that the variables are non-negative and satisfy linear inequalities, which are called linear constraints. Variables are sometimes called decision variables and are non-negative. So we've explained all of those terms, what a linear function is, talked about inequalities, and so on. Some important examples are diet problems, manufacturing problems, transportation problems. There are examples of all of those in the chapter. The common region determined by all constraints, including the non-negative constraint, is called the feasible region. That's the blue area that you've seen in all the problems. Points within or on the boundary of the feasible region represent feasible solutions. So, in general, there are an infinite number of feasible solutions because any point in the blue region can be realized. Any point outside is called an infeasible solution. Although there are many feasible solutions, there are not so many best solutions. The best solution is called the optimal solution. You have two theorems which are basic in solving linear programming problems. Theorem 1 is the corner point or vertex theorem, that the optimum will be at a vertex if it exists. And theorem 2, if the region is bounded, then the objective function will have a maximum or a minimum, depending on what you're looking for. And if it's unbounded, then you can make another additional condition to check whether the solution is in fact optimal. And here are the steps for the corner point method, repeated from the chapter. If two corner points have the same value of the objective function, then every point on the line joining those two corner points will also have the same value. So that's a good summary. And we'll stop there.